Assalamualaikum and good evening. My name is Nurul Huda bin Abdul Rahman, presenter for this paper titled Reverse Engineer 5 Degrees of Freedom Robot Arm Using Programmable Logic Controller. We are from School of Electrical Engineering, UTM. This is the list of slides for this evening. First, introduction, followed by reverse engineer and repair mechanism, robot structure, ladder logic diagram, model, develop control system, develop GUI, result, conclusion, acknowledgement, and reference. To start off, robot arm has been used extensively in the industry to do specific work, to avoid hazardous environment, produce consistent work, and much more. Robots also can be categorized based on their structural properties. Robot arm also have an advantage to reach above and below obstacle and has largest work area for the least floor place. However, a robot arm is difficult to program offline as it has 2 or more ways to reach a point. For this project, we are focusing on pick and place robot arm that have 5 axes, such as pneumatic to get high speed, and motor for higher torque. However, the freedom movement robot is more difficult due to more complex data to read, process, and update it at the same time. There are many methods can be used to program robots, such as using microprocessor or controller. Each implementation has its advantages and disadvantages, such as total system cost, development time, size, power, and axis movement speed. Okay, for this project, 5 degrees of robot freedom arm consists of base, shoulder, elbow, pitch, and roll was reverse engineered and repaired using Programmable Logic Controller or PLC. The original controller was custom made using microprocessor-based system. Since it is impossible and not viable to hack the program inside the microprocessor, the controller is being replaced with a medium to low-cost PLC. Figure 1 shows geometry presentation of 5 degrees of freedom robot arm. The general idea to control axis by observing the motor movement shown in figure 2. Other axes which have similar DC motor will follow the same process flow, which means if there are 5 axes, means 5 flows need to be observed at the same time and appropriate response must be given at the same time. Controller also has to do concurrent processing, which leads to consumption of more processing power. However, too much concurrent processing is not possible when using a low-cost PLC due to limitation of the PLC cyclic scan. Okay, in order to reverse engineer and repair a robot arm, the following procedure needs to be followed, which there are 8 steps of it. The first, need to understand the robot arm structure, list the current sensor, actuators, and interfaces involved. Third, model the controller. Fourth, list the existing function, whether it available, whether the robot arm is still working. 5, list any limitation or weaknesses of the current process. 6, whether anything can be improved. 7, contingency plan. And 8, how to ensure all the objectives achieved. Okay, this is the structure of the 5 degree of freedom robot arm with its main component movement specification shown in figure 3. Each axis controlled by DC servo motor and an encoder. The solution for this provided in RLD model section. Development time to do the reverse engineering and repair was critical for the project, where the team does not have sufficient time to build and proven a stable printed circuit board and interfaces. As a result, PLC was chosen due to its stability, robustness, and readily available interfacing such as digital input, digital output, high-speed counter pulse inputs, voltage level interface, and communication to PC. Okay. This controller is developed using Triangle Logic PLC model with compiler version known as TL41. This PLC contains 16 input and 16 outputs, which all used in the project, and 4 unused ADC channel. This PLC also have 2 dedicated high-speed counter, which are connected to the encoders. Since all 5 encoders need to be monitored, so one of the high-speed counters shared with 2 axes, while the other high-speed counters used for 3 axes. Sharing is possible by storing the encoder data in temporary storage or memory in the PLC. Activities done in several custom functions written in basic language, shown in Figure 4 and Figure 5. Custom function triggered by the input sensor, which mimic the round inputs network. Summary of the LLD model shown in the result section. This method can ensure access can be traced all the time. However, memory read and write are slow process. If all the axes want to move at the same time, data in memory can be skipped due to insufficient cyclic scan time to do the data movement. Since Triangle Logic PLC model cyclic scan is 2 microseconds, each step takes 10 microseconds to execute. For complete applications such as this project, cyclic scan is too slow, especially after adding 96 custom functions, which involves extensive data processing. In order to solve this problem, only one axis can move at the same time. Weakness for this project leads to research team detailed study on PLC architecture, where high performance processor invented to solve the problem. In order to solve limiter between shoulder and elbow, flowchart in Figure 6 is used. A is used whenever the pitch is going to be moved up, while B is used whenever the shoulder is to move down. The actual flowchart more complicated during automatic mode, when the movement of both axes done simultaneously. So the automatic model must synchronize both model, Figure 6A and Figure 6B, at the same time while reaching the target position. For more advanced implementation, signal interpreted Petri-net modeling can be used. Developed control system for this project is shown in Figure 7. This is the dependent controller for the robot, whereby there's an LED display there, LCD display there, that shows the function that user choose. Before starting the dependent of the robot, user need to change manual auto switch to manual mode. This indicates the robot to run in manual mode. This is the look of the developed GUI for this project, where a PC is needed for a more user-friendly operation. Movement of each component can be controlled by the GUI shown in Figure 8, which must fulfill the robot arm movement for each component mentioned in the robot structure section. Since the servo motor and encoder has high precision up to 0.5 mm, encoder reading value is used in the GUI as per in Figure 8 instead of degree of movement, so that user can calibrate the angle on their own. Manual mode also available to use to move the robot to specific coordinate manually. As for result, since the number for timer counter and high-speed counter limited in the PLC, memory storage was used to store the data temporarily, so that same modules can be used for different access in Figure 4 and Figure 5. In total, 60 memory words were used for data calculation and manipulation purposes. Summary for the LLD model is shown in Table 2 as per the slide. Figure 9 shows snapshot of the LLD model, where the input sensor is complicated to keep track the position of pitch and to trigger the correct custom function in the rung at the right timing. Function in figure 10 is used to set the pitch forward limit, where high speed counter 1 will count until the value DM112270, custom function 97 to execute and stop the pitch forward instantly. In conclusion, it is possible to use medium to low cost to low end PLC to control a robot arm freedom movement. Despite the movement is limited to one axis at a time, the system is very stable and reliable as it is inherit from any PLC-based design. The use of GUI on the PC makes the system more user-friendly with option to manually control the robot arm or automatically play back the recorded position. This project is collaboration with WISE-PAS Sdn Bhd and Atamatek Sdn Bhd, whereby the headquarters for the WISE-PAS Sdn Bhd used to do all the works in 2 months' time. Researcher also like to thank research group of VCAT from School of Engineering, UTM. This is the list of reference for the project. That's all. Thank you.